This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on the comparison test. So let's read the formal version of this comparison test. This says let a sub k and b sub k be sequences with positive, that is non-negative terms. If a sub k is less than or equal to b sub k for all k, so the elements of the sequence a sub k are always less than the elements of the sequence b sub k for all k, and if the series, the sum of the b sub k converges, then the sum of the a sub k converges. If a sub k is bigger than b sub k for all k, so the elements of this sequence are bigger than all the elements of that sequence, and if the sum of the b sub k diverges, and remember b sub k is positive, we're adding a bunch of positive things and they're going to diverge. What's going to happen there? Well, it's got to go to infinity. But if you're bigger than a sequence whose series goes to infinity, it's pretty clear that your series is also going to have to go to infinity. So that's the formal statement, but what is the informal statement of this idea? I mean, let's think about what this is actually saying informally. In our first case, what do we have? We have a sequence that is smaller than another sequence. So my sequence here is smaller than a second sequence. So if we think about the series then, my series must be less than the second series. And if the second series converges, if my series is less than a convergent series, then my series is going to have to be convergent too. But I define that less than from looking at the sequence. And regarding divergent, what can we say? If my series is greater than a divergent series, if my series is bigger than something that goes to infinity, am I not going to have to go to infinity? So the really informal idea is smaller than convergent means convergent, bigger than divergent means divergent. So when you're looking at your series, you try to compare it to something where you know how it behaves. So we'll take a look at a couple examples here once we get our informal statement up there. So what will our idea be? We're going to take a look at the following series. The sum as k goes from 1 to infinity of 1 over 5k squared plus 3. What are we going to compare it to? Well, 5k squared is bigger than k squared. Okay, 5 times a positive number is bigger than the positive number. That seems pretty obvious. If I add 3 to that, 5k squared plus 3, I'm making it 3 bigger, is certainly bigger than 5k squared, which is in turn bigger than k squared. So I have my inequality the way that I want to have my inequality. Now just think about this for a second. If I have 7 is bigger than 2, imagine this number is 7, imagine this number is 2. If 7 is bigger than 2, how do 1/7 and 1/2 compare? Certainly 1/7 of a pi is less than 1/2 of a pi. So if I take the reciprocal of this must be less than the reciprocal of that. So continuing with that discussion then, what are we going to say? 1 over 5k squared plus 3 must be less than 1 over k squared. Now these are both sequences, but think about the series. So we know this is true for all k, but the series, the sum of 1 over k squared, is a nice one. It's one we've studied before. What can we say about the sum as k goes from 1 to infinity of 1 over k squared? It converges. By what test? By the p-series test. So what have I done? This sequence is less than this sequence. This series converges. So my conclusion for this comparison test will be that my original series, the sum as k goes from 1 to infinity of 1 over k squared, 5k squared plus 3, is smaller than a convergent series. Therefore, it too must be convergent. So what are we writing here? It must converge by what test? Must converge by the direct comparison test. And again, the idea is smaller than a convergent series with all positive terms. If that's our case, we're going to have a convergent series. Take a look at our next example. Sum as k goes from 4 to infinity of 1 over k minus 2, starting at 4 to avoid division by 0. Certainly k minus 2 is less than k. Everything's positive here. So by the similar kind of argument, 1 over k minus 2 is greater than 1 over k. So, I mean, just to think about that for a second, we're saying 2 is less than 3, but 1/2 of a pi is greater than 1/3 of a pi. Same kind of an idea. But do we know anything about the sum of 1 over k? Sum of 1 over k, that's our harmonic series. Even if it's starting at 4, that's not really an issue. We know the harmonic series diverges. Sum of 1 over k goes to infinity. The harmonic series diverges. My sequence 1 over k minus 2 is bigger than the sequence 1 over k. The sum of 1 over k diverges. I'm bigger than a divergent. So my conclusion will be the sum as k goes from 4 to infinity of 1 over k minus 2 must diverge because, again, that sequence was bigger than the sequence that defines a divergence series. So that thing diverges by the direct comparison test. Bigger than divergent means divergent. So let's see what our next example is going to be. Well, you'll notice I wrote this is the sum as n goes from 1 to infinity of 2 to the n over n plus 5 to the n plus 3. Many textbooks prefer to use n's. Just wanted to show you there's alternate ways of writing these things. But our approach in this course is to use k's and to kind of reserve the n's for the partial sums. So same thing to call it. The sum as k goes from 1 to infinity of 2 to the k over k plus 5 to the k plus 3. Now, here's the real challenge. I want to compare this to something. Smaller than convergent means convergent. Greater than divergent means divergent. All of our terms are positive. So we need to see, is there something we can compare this to? And maybe it's obvious. 2 to the k over 5 to the k is sort of nice. So maybe that's the direction we have to go. So how are we going to compare this? Looking at that denominator. Well, first of all, the sequence a sub k is 2 to the k over k plus 5 to the k plus 3. Looking at the denominator, what can we say about that? We have k plus 5 to the k plus 3 is bigger than a lot of things. Bigger than k, bigger than 3. But the one that will help us the most is bigger than 5 to the k. Because now if I take the reciprocal of both sides, 1 over k plus 5 to the k plus 3 is less than 1 over 5 to the k. Now what? Let's multiply both sides by 2 to the k. 2 to the k is positive, so the signs will not change. 2 to the k over k plus 5 to the k plus 3 is in turn less than 2 to the k over 5 to the k. Do we recognize 2 to the k over 5 to the k? As a series, the sum of 2 to the k over 5 to the k is what kind of series? That thing is a geometric series whose common ratio is 2/5. We know a geometric series with a ratio between -1 and 1 is going to converge. So we'll call that the geometric series test, common ratio less than 1. So you'll notice this thing is less than this thing. That series converges. Therefore, my conclusion is that the original series there, 2 to the k over k plus 5 to the k plus 3, will also have to converge by what test? By the direct comparison test. So that's our idea there. Smaller than convergent, positive terms, means the series I'm starting with must converge by the direct comparison test. So let's take a look at one more example here in this lesson. What do we have? We have the sum as n goes from 2 to infinity of the natural log n over n. Now, do we believe that the natural log n is greater than 1? Well, that's true as long as n is greater than e. So, it's true eventually. Good enough. So, natural log n over n is greater than 1 over n for n greater than e. Do we know the behavior of the sum of 1 over n? Sum of 1 over n? Well, the sum as n goes from 2 to infinity of 1 over n must diverge. Again, that's the harmonic series, just removing the first term. It's still going to diverge. So what I've shown here is the series I'm starting with using n this time. The series I'm using is bigger than a divergence series. So the conclusion that I'm going to make here is what? Is that the sum as n goes from 2 to infinity of log n over n is also going to have to diverge. Why? Greater than divergent means divergent. So what can we say there? We will then argue that that sum as n goes from 2 to infinity of log n over n must diverge by what test? By the direct comparison test. Greater than divergent yields divergent. And that will conclude this lesson.